Hello, everyone. Good morning. So, our lesson for today is about the concept of divide. We are already done with lesson number 1, which is on the methods of proof. So, we're done with direct proof, indirect proof, and also proof by induction. Now, let's go into what really is the concept of divide in number theory. So, we already had the concept of division, but at this point of time, let's go over with what is the concept of divide and try to relate it with the concept of division. Are they the same or are they different? Something like that. So to formally introduce the concept of divide, let's start with the definition. Accordingly, the concept of divide is more on this one. If A and B are integers, where A is not equal to 0, uh, if A and B are integers where A is not equal to 0, take note that you have an A and you have a B, and they are integers in the set of integers. And one of those integers must not be equal to 0, because if it will become 0, then I think it's not possible for the concept of divide to emerge. Then we say that A divides B, written as A like this, B, or others write this A, then B like that. If and only if there exists an integer C such that B is equal to A times C. Let's add if A does not divide B, then we can write it as A and then B and then not divide, we put like that. So if A does not divide B, then you can write it this way. So let's have an example. We have for an example, if we will read this one, this is 2 divides 6. Is this true or false? 2 really divides 6 or not? So let's try. According to the definition, example, if this is our A and this is our B, we will have this one, right? Okay. So if we can write B equal to A times C, meaning our 6, if we can find a number, the A is 2, if we can find a number where we can multiply to 2 and we can get 6, then it's true. And we can get an integer 3, right? Therefore, 2 divides 6 is correct. No, it's true. So what we did is we look into, let's have it clear. 2 divides 6 since there exists. So you can have the symbol as there exists. There exists an integer 3 such that 6 is equal to 2 times 3. Like that. So we try to go with that. Let's have another example. How about 4 divides 12? Is this true or false? Okay, so what we will do is we will look at a number. So 12 is equal to 4 times a certain number. What number can we multiply to 4 to make it 12? We have an integer 3. Therefore, this is true. How about the reverse of it? 12 divides 4. Is it true or false? Therefore, we will look into 4 is equal to 12 times something to get 4. But if we will look into that, we need to have 1/3, right, to get 4, correct? And 1/3 is not an integer, not integer. Therefore, this is wrong. So does not divide. 12 does not divide 4. How about the example 5 divides 0? Is this true or false? Okay, 0 is equal to 5 times a certain number. What number can you multiply to 5 to get 0? It is 0. Therefore, this is true. Because 5 times 0 is 0. So there exists an integer 0 such that x is equal to 5 times 0. Or I mean 0 is equal to 5 times 0. So I think we already have the basics on divide. So I think our question now is it different to the divide that we have? For example, let's have this one. If you say 12 divided by 6, is it the same with 12 divided 6? Let's check. If we say 12 divided by 6, we can have 2, right? But if we say 12 divides 6, this is wrong. It does not divide. But if we will write it as 6 divide 12, 6 divides 12, I think this is true, correct? Because we can find a number 2 on that. So on that manner, when you say 6 divides 12, I think it's a similar manner on 12 divided by 6, something like that. But the divide is you look for an answer, but the 6 divides 2 is just, I think it's a concept, no? That you can check whether it divides or not, something like that. So based on this definition, we can have some remarks. The first remarks that we have here is that A and C are co-divisors or factors of B. Let's go back with our example. If we have A divides B, that implies that B is equal to A times a certain, some integer C. So this A and C, this one and this one, these are called as divisors or factors. For example, if we have 5 divides 10, that is just equal to 10 is equal to 5 times 2, meaning if we have 10, its divisors or factors are 5 and 2, something like that. And then next, B is a multiple of A and C. Let's check. Our B is 10. So let's check if it's a multiple of 5 and 2. We can say it's a multiple, we just have to skip count. So 5, 10, 15. Correct. 10 is a multiple of 5. How about 2? 2, 4, 6, 8, 10. So we can see in this example that 10 is also a multiple of 2. Now let's go for the remark number 3. B is divisible of A and C. Is it correct that B is divisible of A and C? Let's check. 10. Is 10 divisible by 5 and 2? Let's check. 10 divided by 5, that is 2. Check, divisible. 10 divided by 2, that is 5, divisible. That's correct. B is divisible by A and C. Fourth, any counting number is a factor of itself. Why? Like 10. 10 is a factor of itself because you can have 10 times 1, right? So you can always have a factor of itself and 1. Same thing with any counting number is a multiple of itself. Because if you skip counting, you start with itself, 10, 20, 30, something like that. So you start with itself. So it's still a multiple of itself. For number 6, 7, 8, and 9, there's a need to prove this one. So let's start to prove with the number 6 and number 7. 8 and 9 will be given to you as an assignment. So for number 6, if A divides B and B divides C, then A divides C. The second is if D divides A and D divides B, then D divides A and B, or A plus B. The number 8, if D divides A, then D divides C times A for any integer C. And the last one, if D divides A sub 1, D divides A sub 2, and so on until D divides A sub n, then D divides C1A1 plus C2A2 plus it goes on until say CNAN. So let's try to prove number 6 and number 7. We will use another screen. Okay, if A divides B and B divides C, then A divides C. Okay, let's prove this one. So I think we need to make use of direct proof, right? Let's just make use of the definition. Okay, suppose A divides B and B divides C. By definition, when you say A divides B, it implies that there exists an integer, let's say x, such that B is equal to A times x, correct? In same manner, if we have B divides C, it implies that there exists an integer y such that C is equal to B times y. Okay, since B is equal to A times x, then C is equal to B times y can become C is equal to, you put this one A x into B. So change that to A times x, and then we have y. Then C is equal to, because we wanted to have A divide C, so we need to separate A here and we can combine x and y. So with this, if you have, you can just let, you can have Z is equal to xy for some integer Z. So you can have here, then C is equal to AZ. Thus, A divides C. Based from this one, if you transform that like this. So I think we're done with the proof. No? We were able to prove that if A divides B and B divides C, then A divides C. Let's go into the second theorem that we have. Let's prove it. So let's try to prove that if D divides A and D divides B, then D divides the sum of A plus B. I think this one. Okay, this is it. Similar nature, I think we can make use of direct proof. Let's make use of definition. So suppose D divides A and D divides B. By definition, when you say D divides A, it implies that there exists an integer. We can have x such that A is equal to D times x. In same way, if you have D divides B, it implies that there exists an integer. We can have y such that B is equal to D times y. So looking into that, we have this and we have this. Then, if we add A plus B, then we can say that dx plus dy, right? This one, A plus B. So you can have dx and dy. So if you have A plus B, you can put the d outside. You can have x plus y because we wanted to have this. Oh, wait. I think my screen. Okay, so if we have b and dy here. Now, we wanted to have this. D divides a plus b. We already have d and we have a plus b. We can just have let x plus y. So let x plus y is equal to z for some integer z. Then we can have a plus b. Then a plus b is equal to d times z. Thus, d divides a plus b. Look at this. I think we're done proving it. So I hope in our next meeting, you will be able to prove the remarks 8 and 9. I think that's all, and thank you.